Okay, it's a pleasure to introduce the second speaker of this morning, Frank Goehmann from Wuppertal, and he will speak about the thermal form factor expansion for the correlation functions of the XXZ chain.
Yeah, good morning, everybody. I'm very happy to be here. Thanks to the efforts of our organizers, I'm happy to see, well, living people in front of me, which I missed for the last 2 years mostly. My subject today is something I've been talking about many times, and I hope to, well, today I think I'll be able to report some progress in this subject. It's about correlation functions of the XXZ chain, and now it's not moving, it's moving slowly, just slowly. Good, let's move slowly. As Filippo pointed out to me, this is a rather diverse audience. Diversity is a big subject nowadays. So here diversity means randomness, integrability, and universality. So my talk will be mostly about integrability, a little bit of universality inside. And because the audience is so diverse and because Filippo asked me to do so, I'll stay on a descriptive and introductory level with everything. And especially I've added a few slides at the beginning for those who are not working on quantum integrable systems, just to set up the stage and tell you what I'm interested in and why this might be interesting for other people. And then I'll explain you our techniques, the thermal form factor series. So, well, this is I'll talk about dynamical correlation functions of quantum integrable models. And there's actually not so much known about dynamical correlation functions for integrable lattice models. And all the useful results I know are based on form factor series expansion. So expansion in terms of matrix elements, or there enter matrix elements of local operators between, say, ground states and excited states. But there's still a lot of choice. The choice is in the basis in which you expand, and there are different bases, though usually people expand in the Hamiltonian basis. And our approach, the thermal form factor approach, uses a different basis, which is the basis of eigenstate of what we call the quantum transfer matrix. I'll explain you what it is. And since we use a different basis, we get a different series for the same things that people also looked at. But different series may be, well, of different use, and they may have different properties. Think of, say, for instance, theta functions, elliptic functions, where you have modular transformations. So you may have series which are very well numerically convergent in one parameter regime and not so well in other parameter regimes. And I think our new series have very nice, they do have very nice convergence properties. And actually, first I thought I would talk for an hour, and there was a part about the XX model. For the XX model, we worked out the full thermal case, and there is another representation we could compare with, which was obtained a long time ago by XXZ, Zergin, Korepin, and Slavnov. And these series have completely different asymptotic properties. So our series has the property that in the space-like regime, the first term in the series determines the asymptotics. So we can obtain the asymptotics by simple subtle point analysis and don't have to use more elaborate matrix Riemann-Hilbert techniques. Since there's not so much time as I expected, I'll skip that part and only talk about the second part, which is about the XXZ chain in the massive regime, delta larger than 1, magnetic field below the critical field, and the limit t to 0. This is also a case which has been studied by several people, and the new thing will be that we get fully explicit series. It means, well, the series you can expect is a series of multiple integrals, and as compared to previous results, the integrand is explicit in terms of known special functions, and it's just a single combination of special functions. It is explicit for all numbers of excitations. This is the new point, and you'll see how it looks like. So then I'll summarize and discuss. And this work is, so this part of the work I'm going to talk about today is based on collaborations with my long-term collaborators, Karol Kozlowski from the ENS de Lyon, Junji Suzuki from Shizuoka University in Japan, and also with contributions from our postdoc, Konstantin Babenko, who stayed in Wuppertal for 2 years, and Jesko Zirker from the University of Manitoba. So this is for the people who are not in the field, and I think there's quite many. So I am doing statistical mechanics of quantum chains. A quantum chain is something like a fully regularized quantum field theory. So everything is finite. You have a finite lattice and a finite Hilbert space. So the dynamics on this space is just generated by a Hamiltonian sum Hermitian operator acting on this space, which is say is a tensor product of finite dimensional spaces, and we can define local operators which act as an endomorphism X just on one of the factors in this tensor product. Of course, you can also have local operators of longer lengths where you have non-trivial action on 2 factors or 3 factors and trivial actions by identity on the other factors. And with these ingredients, we can define quantum statistical mechanics. So there is a dynamics which is generated by quantum mechanics, the Heisenberg time evolution, which is the adjoint action of the time evolution operator e to the I Hamiltonian times t. And then there is density matrix. Here I showed the canonical density matrix of Gibbs ensemble. So this allows you to say evaluate operators acting on this Hilbert space to some real numbers, and this is what you measure in experiments. So more generally, there is something in theoretical physics which is called linear response theory or Kubo theory, which connects the response of a large quantum system to finite time-dependent perturbations, which are experienced, and they connect these the response with dynamical correlation functions at finite temperature T. And those are typically such 2-point functions. And let us look at the intuitive meaning of this. So what does it mean to have a 2-point function? The main example is when the 2 operators are Hermitian conjugates of each other. So X is the Hermitian conjugate of Y. Then having any such expectation value means you average with respect to the eigenvalues of a density matrix, so non-negative numbers summing up to 1. Such scalar products where you have the operator Y, which acts only on one factor, so we say on one lattice side, on some quantum state, and then you time evolve it, and the averaging may be done with the canonical density matrix. So what you have on the right-hand side is you create a local perturbation at side m+1 by means of this operator Y, then time evolve it for some time t with the time evolution operator. And on the left-hand side, you do nothing, so the system is time evolving automatically by itself. So you wait. This means you apply this evolution operator on the state, eigenstate, and then after time t, you create the same local perturbation at side 1. So then, taking the scalar product in quantum mechanics, if you look, say, in the Feynman lectures or something like that, means, well, if you have a scalar product A, like between 2 states, psi and phi, it means to measure psi once you have prepared phi. So here it means it's the probability amplitude for observing a local perturbation y at site 1 at time t once it was created at site m+1 time t ago. So the probability amplitude for the propagation of a perturbation. This is the meaning. I'm familiar to those people who are working on that, of course, but as I said, not everybody is doing it, so I wanted to explain this again. So that is correct, yes, because it's a trace, yes. So we want to calculate such objects, correlation functions for integrable models, and here the prime example is the XXZ model. This is, in a sense, the simplest integrable lattice model, and we are still very much at the stage of developing methods, so it's clever to stick with the simplest models. And at the same time, it's a model which is very prominent in quantum magnetism, at least if you not restrict yourself to 1D models, it's all over in theory and also in experimental work on quantum magnetism. So here the model has two parameters, an anisotropy parameter delta and well, 3, 1 over energy scale, then an anisotropy parameter delta, and a magnetic field along the anisotropy direction. And the only thing here which is important for the later part of the talk is the parameterization of the anisotropy. It's in terms of a parameter either gamma as cosh gamma, or we use the parameter q, which is e to the minus gamma. Okay, so these numbers q and gamma will appear in the formula later all over. So the main goal of my research is to calculate two-point correlation functions like between two Pauli matrices at site 1 time t, site m+1, and time 0. And there are many more, so where you have, say, local operators ranging of several lattice sites. So we would like to develop a theory which allows us to get all these expressions explicitly for all values of distance, time, temperature, anisotropy, and magnetic field. That's the goal. And unfortunately, the state of the art is that dynamical correlation functions at finite temperature are not known exactly, except for the case when this delta, the anisotropy, is 0, and this is the so-called free fermion point where the model is more simple. So here is an example at the free fermion point. I show you this example for several reasons. This is actually, well, when delta is 0, we call it the X model. So the XX model, the so-called longitudinal correlation functions, as ZSZ correlation functions, are known since the late 60s. This was first calculated by Niemeyer in 67. But for us, for our, say, new method, it was also the first thing to be reproduced. So if you use the thermal form factor series I show you later, you rather immediately get the following expression, the following nice form of correlation functions. This is just a double integral involving two wave factors, which can be interpreted as holes and particles evolving in time, and an amplitude, which here in this special case factorizes into, say, two Fermi functions of particles and holes. And this epsilon of p is the energy. So this is so simple and nice. So this is the kind of things we want to have. Simple, nice, and explicit formula, which allows us to calculate the correlation functions at all m, t, temperatures, and magnetic fields. And here, well, you can just plug it into some computer mathematics system as Mathematica. You get the black curve. And you can as well do a saddle point approximation. Then you have two regimes, the space-like and the time-like regime. And so the saddle point approximation does not work well at the Stokes line where the two regimes match. But outside, it basically gives you the correlation function, well, with very high precision. And this is the goal also for all other cases. We want to have such pictures. Yeah? And well, although, and what I also showed this for another reason, so although this is a very simple case and the formula are much more complicated in other cases, the qualitative behavior will be the same. So what happens is you perturb the system, you're sitting m sides away, and then the perturbation is propagating. It's like you sit in the boat in the pond and the frog hops into the water, then it will create a wave and you wait some time. The wave has some propagation velocity, so you will see the wave coming to your boat. This is the big wave, and the wave, because the water surface is an excitable medium, the wave pulls after it the ripples, small ripples, and this is the general picture you expect. Okay, so this was the general introduction for the general audience. You may see, say, it's not phase transition, but crossovers between different asymptotics are different in different, depending on the parameters. Yeah, so for instance, the asymptotic analysis, yeah, it may be different. So it may be saddle point determined or determined by poles. There may be many, and it may change if you vary the parameters. Yes. Yes. It's the 2-point, no, it's the 2-point function, just this one, sigma z, but I subtracted the square of the magnetization so that it goes to 0 in the limit. Yes. Yes, it's linear response. Of course, I mean, many people in the audience are now interested in much more, say, general things, nonlinear response, non-equilibrium. But what I say for these integrable models, even for the equilibrium linear response regime, not so many things are known if you're thinking about dynamics and if you're interested in having exact results, not approximate results. That's my claim. Yes? Pardon? Oh, so actually nothing happens. It's just what the black line is just the integrals calculated numerically. Yes, that's the formula. But it's still an integral, and you would like to have, say, an approximation to the integral, which is just a formula, some f of something, and f is some known formula. And you can get that by doing here a saddle point analysis of the two integrals. If you do a saddle point analysis, then you typically have the problem that, I mean, you look at the saddle points, and then there are situations where the saddle points sit on the real line and then the complex plane, so you have different regimes. And so then the asymptotic changes. It changes here actually from exponentially decaying to oscillating and algebraically decaying, and these crossovers in the world plane MT, there's a crossover line, it's called the Stokes line, and at the Stokes line, the saddle point approximation, linear order or first order saddle point approximation does not give you good results, but you can go to higher saddle point and so on, and then you can also say something about this. But this is already some more involved asymptotic analysis. So let's, yes. And, so, well, that is just an example of what we want to know. Okay, let's go now I try to explain you the method. The method is, we call it thermal form factor expansion, but the first idea is to present dynamical correlation functions in a good way using the integrable structure. So here's a picture which can be interpreted in two ways. So you see we have lines which are crossing, and every line crossing here is an R matrix of a vertex model. This is one explanation or one interpretation of the picture. So you have product of many R matrices here. Each of the R matrices satisfies the Young-Baxter equation, and for this to work, I use R matrices which are where the spaces are the same. I mean, so-called fundamental models and which have the property that evaluated at spectral parameter 0, they are the permutation. This is all what we need for this to work. So this is a special vertex model with two insertions representing the operators x and y. This is one way of looking at it, and we apply, so here is a gauge field, and then we apply periodic boundary conditions. So we connect the top and tail of these lines periodically in the vertical and horizontal direction. So for a physicist, the meaning of this is lattice path integral. So here time goes up, space direction goes to the in the horizontal direction, and every point here is a space-time point, and you sum over all vertex model configurations, so over all fields. This is really a path integral, and if you insert R matrices with the properties I have told you, so fundamental, which reduce the permutation, then the product of these two transfer matrices, the double row transfer matrix, is proportional to E to some Hamiltonian. Yeah, and so here's the spectral parameter I divide by n. So if n large, this is small, and this is really the infinitesimal generator of time translations in this case, for a proper choice of this parameter tr, and n to infinity. So then I multiply n over 2 such infinitesimal operators, and if I do that and send n to infinity, this is really the time translation operator. So you get y, time translation, x, then here I translate in time and in imaginary time, which gives me access to finite temperatures. So this is the picture, and then the question is, how can we make use of it? So this is most of the people look at this object, the double row transfer matrix or usual transfer matrix, but you can also just compose it by multiplying those transfer matrix, and this is what we call the quantum transfer matrix. Fyodor calls it Matsubara transfer matrix. Anyway, there are different words which depend on your background. So this quantum transfer matrix, this terminology, which is not especially, how to say, lucky, was introduced by Masu Suzuki, who is one of the protagonists of this, say, quantum statistical mechanics, or who used to be one of the protagonists. And Matsubara, of course, comes from field theory. So we call it the quantum transfer matrix. And this has eigenstates psi and eigenvalues lambda. And important for us will be the ratios of, eigenvalue ratios, eigenvalues pertaining to excited states, and the states, the ground state, which we call the dominant state here. So you may wonder why we are using it, and so this is for the people who know about beta ansatz, but not so much about this quantum transfer matrix. So there are two transfer matrices, but they are different. One is staggered, the other one is not staggered, and they have rather different properties. So this double row transfer matrix gives you the generator of time translations. The quantum transfer matrix does space translations. Then we have periodic boundary conditions and space directions for this double row transfer matrix, and using periodic boundary conditions in space direction, you get quantization conditions for the momentum, which are called beta ansatz equations. When you do it in this quantum transfer matrix case, you got, for small t, you get quantization conditions for the rest energy. So this corresponds to the Wick rotation on the lattice. So you're quantizing momentum here, energy here. Here, the Hamiltonian Hermitian has real spectrum. There, the transfer matrix is non-Hermitian, has non-real spectrum. Here, the beta roots are continuously distributed in the thermodynamic limit. Here, it is not the case when t is finite. At every finite t, the beta roots distribute, give a distribution with a single accumulation point. And if you want to describe this part, you have to use nonlinear integral equations. Here, you can work with linear integral equations. So what we are doing then is, let's go back one step to this picture. We express this, oh, sorry. No, that's not what I wanted. Tick, 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 tick. Press the wrong button. Sorry. So we express this partition function entirely in terms of matrix elements of eigenstates of the quantum transfer matrix and these eigenvalue ratios. Yes. So this is shown here, and we, the operators X here are products of local operators, Y products of, also products of local operators here ranging over L for left lattice sides, and here we have a number R lattice sides, and we assume that these operators have definite spin, so there is a U1 charge such that they are eigenstates with respect to this charge in a joint representation, and the number here is called the spin. And so with this, you'll get the following formula. So this thermal correlation function of operators X and Y is some trivial p-factor, and then the sum over all excited states of the quantum transfer matrix. And here are eigenvalue ratios, time-dependent, raised to the power n over 2. N is sent to infinity. Here is the time dependence inside. And here is the space dependence, again in eigenvalue ratios. And here you have some matrix elements of monodromy matrix, of the monodromy matrix between beta and such eigenstates. So then the hard work is to compute these things, to sum them up, and to do the limit when n goes to infinity. And doing this, explicitly, is not easy. We can transform this into, say, a formal series involving solutions of nonlinear integral equations, but this is still not of a form that it can be really computed or is good for asymptotic analysis. For the latter, at the moment, the latter can be done just in the special situation when we send temperature to 0 and when we are in the massive regime. And I just want to show you the results now, okay? And it takes some time because the formula also needs some contemplation. So first of all, what we get here, the dynamical two-point functions of spin 0 operators. Remember, I explained you what the spin is. It's the change of spin a local operator does. So dynamical two-point functions of spin 0 operators for the XXZ chain in the anti-ferromagnetic massive regime at temperature 0 have the following form factor series representation. It's instead of a sum over all states, we now have a sum over all classes of states. So classes of states means the physics series scattering events. So, and for spin 0, you have an even number of scatterers. So you may have one particle scattering one hole, 2 particles scattering 2 holes, 3 particles scattering 3 holes, and you sum over all possibilities from, say, 1 particle 1 hole to infinitely particles infinity many holes. And then you have 1 integral per particle and 1 integral per hole. Here is a wave factor, and here is an amplitude. The wave factor factorizes, but the amplitude couples the particle hole degrees of freedom. So if you have just 1 integral, this is what you know, say, from electrodynamics in media. So you have a wave and some amplitude. You may analyze this. This is typical wave propagation. But here you have multiple waves which scatter each other, and the interaction is described by the amplitudes. So our result now is, maybe I should also say that also the integration contours here are simple. Basically, the interval minus pi on 2 to pi on 2 shifted a bit up or down in the complex plane. So this is also simple. Okay, so these amplitudes is the new things. The blue thing, we were able to get explicit expressions for these amplitudes, and so far we worked out two cases. One is when x, the operators x and y are two Pauli matrices, sigma z and sigma z, both the same. And the other case, which is in the preprint, is when we have a two-side operator here, which is also spin zero. So we take for the amplitude this minus plus, minus plus minus, okay? And we have to multiply by I in order for this to be Hermitian. This operator is the spin current operator, or the spin current density. Okay, so let's first have a look at the dispersion relation. Dispersion relation P and epsilon. So this function P is something you know from your mechanics lecture, elementary mechanics lecture. If you have a mathematical pendulum and look at the angle as the function of time, it's the same as for P. P is the angle and lambda is the time. So it's when it goes around. So when the energy is large enough that it goes around, and it's linearly increasing with a periodic modulation, and this is this function. This function is a dn function, which you know as soliton trains in Korteweg-de Vries equation or something like that. So some nice functions, and in particular you can plot it. And if here you have epsilon of p, it's the solid line here. It's a dispersion branch of holes, and this is reflected. So you can, if you multiply by -1, you get the dispersion of the particles here. And as you see, you have a gap, a mass gap here, and delta is 0.5 is already pretty small. When delta goes to 1, it closes, and you go to the, say, conformal case here. Okay, so for the, well, just some notation. So we always have sums over all particles and all holes, and they come with different signs. So we introduce this shorthand notation. Lambda and u minus v means sum over all lambda and u minus sum over all lambda and v, so particles and holes. And the same for products, only, yeah, it's like for the logarithm here. Okay, this is our notation, which I have already used. And then the first thing is that these amplitudes, they factorize again in a part which depends on the operators, and a part which I call a weight or universal weight function W. So the part which depends on the operators is simple when the operators are short. As you see, is in particular, here you have squares and you have the same operators. So in a sense, 1 sigma z corresponds to 2 sine of, and then basically the sum over the differences of all momenta. And if you take the other operator, you get sum of the differences of all energies here. So this is a simple factor, and the fact that it is simple relates to the fact that the operators are so simple. If you go to longer operators, then well, I'm sure that what you'll find, and I have good reasons for that, I can comment on that. So what you find when you go to longer operators, you find structure of factorized correlation functions, which is the same as, I mean, you find the fermionic basis structure introduced by Hermann Bose, Jimbo Mivasmanov, and Takayama in these beautiful papers. So there will be two functions, usually called rho and omega, which characterize this operator-dependent part. And here in this simple case, this is the case where omega doesn't appear. It's the case where you rely only on rho. So this is, so in a kind of, from this point of view, it's the kind of trivial correlation functions. But this part here, this is not covered, as far as I understand, by the fermionic basis, but this is universal. It depends only on the spin, and for all spin zero operators, it will be the same, and this is what we calculated. And let me show you the formula. Formula is a bit lengthy, but not too long. But the main point is that we have only classical special functions here. So the main part are basic hypergeometric functions. So you may know the, well, probably almost everybody knows the Gauss hypergeometric functions F21. And this is generalized to generalized hypergeometric functions Fmn. So it's just like, it's a generalization of the series of the exponential series in the sense where you have ratios of Pochhammer symbols in front, and you can Q-deform it by replacing Pochhammer by Q Pochhammer symbols, and you get these basic hypergeometric series. Anyway, these have been studied by mathematicians for a long time. They were introduced by Eduard Heine in 1846 in his Theorie der Kugelflächenfunktion. So this is something really classic. Yeah? And so they play the main role here. And you see they have these 2L, they have, if you have index Mn, they have M plus N parameters, and this is something we need. We have 2L particles and holes, and we need a multi-parametric function to describe them. This is the type of function. So then there is another function psi, which we obtain by multiplying one of these combinations by a rational function. And then another shorthand notation, we'll also have the same thing where x is replaced by minus x, y by minus y, alpha by minus y, and we just write a bar to have short notations for that. Then here's the core part of our formula for the universal weights. It's a matrix, finite matrix with matrix elements. On the diagonal, they are combinations of this phi1 function and phi1 bar, and off diagonal of the psi. And there is another factor here, which is just a product of Q gamma functions. Sigma is the sum of differences of particle and hole rapidities. Then m hat is obtained by replacing xj by minus yj and vice versa. And there's another function xi, which is again a ratio of Q gamma and Q bound function. Of course, you cannot grasp this so quickly, but you can grasp that this is just some products of known special functions and something you can type into a computer if you want to get the number. You don't need to know anything. You can look up the definition of the formula. Some of them are implemented into Mathematica, and you can plot this and calculate the integrals. That is my point. So you put these things together and get the universal weight. It's just a ratio of theta functions, then this function psi appears, then two determinants and a Cauchy determinant. That's all. Yeah? And this is so nice that you can really calculate it on a computer, at least the first terms in the series. So what you have to do on a computer is, since it's a rapidly oscillating integral, you have to numerically implement saddle point integration in order to calculate this precisely. And this has been done by my colleague Junji Suzuki. And you see here, this is for the sigma z correlation functions, and again this long range part subtracted, so side 1, side 3, and here's the time, and here's the real part of this correlation function. And then the red dots give you the contributions from the first integral, so the double integral, the green dots from the quadruple integral plus the double integral, so you add up things, and the blue dots is what you get when you add up the triple integral, so six-fold integral contributions. And what you see here is that basically, well, the higher integrals do not contribute for long time. So the long time asymptotics is given by just by the double integral. This is what you can see here. And you can do a saddle point analysis and get some explicit expressions for this double integral, just the formula you can write. And so then, but numerically, you can also use these formula. You can go to long times, and we have compared here with time-dependent DMRG, which goes, say, up to here. Jt is equal to 10, maybe a bit larger. But with our formula, you can go to very long times, also to large distances here, and just follow the correlation. And you see qualitatively, it looks the same as in the XX case, just this bump and then a ripple of correlations. So here it's for very long times, 250, and you see an odd-even effect between these correlation functions. The second figure shows you a comparison between the numerical result, which is the black line, and the black line is what you get from a saddle point, and the dots are from the numerical calculation. And again, you see for long times everything is determined by the saddle point values. And since we can go to very long times, we can also Fourier transform the data and get what is really observed in the experiments, which exist for these spin chains. So we get a so-called dynamical structure factor, and you see, since we can go to very long times, the Fourier transform really resolve these singularities, and it was known, of course, that well, you have an edge singularity for wave vectors below pi on 2, and it vanishes when you are between pi on 2 and pi. And all of this can be obtained by numerically Fourier transforming these data. So here's something rather recent. As I said, the formula for the current correlation function looks almost the same. It's no more complicated. Instead of sine square of p's, you have square of sums of energies, and both of them are explicitly given in terms of Jacobi elliptic functions or Jacobi theta functions. So it's equally simple to apply this to the current correlation functions. For the issue of conductivity, the interesting thing is to look at the correlations of, say, one point, current at one point, with the sum of all other currents. This is actually something like the zero wave number component of the correlation function. So, and here we have summed up the first 350 terms, and well, what you can see here is that you can do it, and that the structure is not trivial. It's not, yeah. And you can also Fourier transform these data. These are the blue dots. The blue dots are the numerically Fourier transformed data just for the first integral, so one particle, one whole scattering. And in that case, you can also do the Fourier transformation analytically, and this is this curve here. So what you can see in the left picture is that the Fourier transformation, I mean that the data, the time-dependent data are very accurate. So this is a naive Fourier transformation without any filtering or throwing away points. And of course you expect some problems at very low frequencies which come from the cutoff. And but even while these very sharp features are resolved. And with the analytic formula, you can get, well, it's a simple formula I show you, you can just plot this, say, I did this using Mathematica. So what you can plot here is the real part of the dynamical conductivity, is the transport quantity, which can hopefully be measured in these spin chain materials. And here is just for, well, if you do this Fourier transformation analytically, you better express some parts in terms of Jacobi elliptic functions, so then you need the elliptic integral of the first kind and the elliptic module and the complementary one, and they are both expressed in terms of Q using theta functions. And arc Sn is the inverse Jacobi Sn functions, and these are again Q Barnes functions. So those are the functions we need, and we put them together and get an explicit formula for the two particle, so one whole, one particle contribution to the dynamical conductivity, which is pretty simple, I would say. So the function B goes in here, and the function R. This is something which looks single. So this comes from the density of states. You see here two Van Hove singularities, which go like 1 over square root of omega. But in the picture, there are none. So they are cancelled by zeros of the form factor densities here, which shows you that to get the full picture of singularities, it's not enough to look at the density of states, which many solid state physicists do, but you also have to look at the form factor densities. So this is all I wanted to tell you. We have applied the thermal form factor approach to the dynamical two-point functions of the magnetization and of the spin current for the XXZ chain in the massive antiferromagnetic regime and in the low T limit. For T to 0, we have obtained explicit expressions for the form factor amplitudes that contain only finite determinants. So kind of nice practical formula, which can be used by people who don't want to know about the theory. You can just take them and plot things and compare with whatever you are interested in. So the resulting thermal form factor series for the two-point functions are numerically efficient. And finally, well, there's of course much to be done, and this is hopefully just the beginning of something. The future work we want to do is, first of all, in this line, there is the series, well, there will be a series of all spin zero operators, and we have to well, calculate the function omega and look at the relation with the fermionic basis approach of Bose and others. And then, of course, the next step will be to extend this to higher spin operators. Then this universal part will change. Yeah, and I would be curious how it looks like. A thing which we are working on with a lot of effort with a PhD student of mine and with Carol is to extend this to the massless regime of XXZ. I can comment on this if you are interested. And then we have now we have a series which is rather conventional, a series of multiple integrals. I think some of you working on more mathematical questions are familiar with such things, and you wanna well, understand this mathematically. So the first thing would be to show the convergence of the series, which is, I think, now in reach. Then you want to estimate the truncation error and turn this into some function. Yeah? And we will also work on this. And then we want to obtain the isotopic limit and perform the long-time large distance asymptotic analysis of two-point functions of the XXX chain. And finally, which was actually our original motivation, of course, we want to go to finite temperature. And here, probably the first step would be to go for a high-T analysis of the correlation functions. Thank you very much.
Thank you very much for a nice talk. Are there any questions?
Yes, so the one spin, I mean, the first integral contribution looks very much like the XX result. I mean, at least the large time
yes,
decay,
the
no?
whole thing, yes.
So could you, I mean, I don't know, the saddle point of it, can you still write it in terms of, I don't know, simple Bessel functions or?
Not in terms of Bessel functions, but in terms of something simple. It's not Bessel functions, yes. Yeah, you have all these Q gamma and Q bars functions in it.
Okay, but you didn't write it here.
I didn't write it here, but yes, just I can show it to you. Yes, it's in at least in one of the papers. I think we didn't write it for the sigma z correlation functions, but we wrote it in for the current correlation functions.
Yes. Yes, I was just wondering, what is the, how do you define this form factor density? What is it?
Form factor that is just what you have in I mean, the point is, I mean, if you go from the why I call it density. So you start with a sum and go from the sum to an integral, and the individual summands in the sum, they scale like um, like 1 over L or something like that, but this is just what you need to turn the sum into an integral, and that's why I call it density. You have the, see, let's go to the formula. Yes, go back, go back, go back. No, this was this what I wanted to show you. Yeah, so here is the sum. This is a sum over some, say, beta ansatz data. It's when n is finite, this total number. This is just a finite sum, and you want to do this limit when n goes to infinity, and also the limit when t goes to 0. So then this sum turns into an integral, and you get some measure here. I mean, you have to say scale this by the length of the system or something like that. Actually, it's a bit more complicated because it goes through these solutions of nonlinear integral equations, but basically it's that. So the individual form factors may vanish, but the sum does not. And that's why I call it densities.
I was just wondering about the massless case.
Yes.
I mean, are you able to do non-zero magnetic field as well?
No, that's a very good question. So one of the reasons why this works is that we start with finite magnetic field. And so this is all based on an analysis of the beta ansatz equations, which is also the non-rigorous part, as usual. So analyzing the beta ansatz equations, and we have some conjectures on the behavior of all solutions. We need all solutions of the beta equations. And the conjecture, which is a strong conjecture, I can explain you why. The conjecture here and on which this is based in the massive regime is that if you have a finite magnetic field, and the results even do not depend on the magnetic field, but we need a finite magnetic field at the beginning. If you have a finite magnetic field, then there are no so-called strings in the solutions of the beta equations. So all strings go away in the limit t to 0. So keep H magnetic field finite, send t to 0, then the strings go away. Somehow they fly to infinity. And I can explain you maybe privately how this works. And then the question was, is it a feature of the quantum tensor matrix or a feature of the massive regime? Both might be possible, but we believe it's a feature, well, something related to both. So what I believe now, and we have already say strong arguments, is that when delta is larger than 0, so in the massive, say, so-called repulsive regime, this feature still holds. So if you have a 0 magnetic field, then the strings will go away and the limit t to 0. But when you're in the attractive regime, delta between -1 and 0, strings will appear. And they become more with, so the conjectures, they become more with the roots of unity. So between delta between -0.5 and 0, there's a 2 string, and between, well, I can't express it in delta, but in this gamma between, say, when gamma is between 3/4, so 2/3 and 3/4, you have 3 strings and so on. So it's something like in the Takahashi-Suzuki picture. And then if you have no strings, then similar things may become possible.
Some further questions?
Please.
Show me this beautiful slide with oscillatory behavior of linear response function.
This one?
Yeah. So XXX, beta XXX is a very correlated system.
Yes.
And
Yes.
So the question of comment. Would you have a semi-classical parameter like a large spin, and then compare how this picture is deformed by increasing spin? The expectation would be that the deformation would be almost invisible. Perhaps it's quantum, because spin is one half, but perhaps the whole thing very close to what would be classical. By simply solving nonlinear equation for one each.
Yes.
Nonlinear equation for
Yeah, but still, the questions about the.
It actually would be a very crucial test.
Yes. So highest.
Let me make one comment. If you consider XXZ
Yes.
and write an isotropy to the three particle case limit XX problem,
Yes.
then it will be very, very quantum. Although three parts.
Yes.
But if it is XXX different limit, very correlated, it must be semi-classical. That's an expectation. That would be an expectation.
I'm not so much sure about, say, zero temperature, but so my proposal would be to go to a high temperature. Then it should become zero temperature.
Zero temperature, but perhaps large speed.
Yeah.
Larger speed.
Well, you know, for large spin, if you look at the integrable large spin models, they are a bit different. It's not the naive generalization. You have these polynomials in. So the integrable case.
Just to have a semi-classical parameter.
I see. Yeah, this is thinkable, but it is not easy to go to higher spin, for instance, with this factorized part. Fyodor will be able to tell you something about this. They worked out the spin 1 case, but for the general case, maybe still some work to be done. It's not a big deal. Yeah. So
It could be a very interesting test with the general idea that if the system is very correlated, it's described by hydrodynamics, and hydrodynamics is very simple. Mathematics is like this sort of aerodynamic. It doesn't describe the hydrodynamic. But you don't have hydrodynamics like that. Whatever it's called, nonlinear equation for. Let's discuss. You don't have.
Some further questions?
So this ratio of elliptic functions you're subtracting from your 2-point function, is that the disconnected bit? Is that the 1-point function squared?
Not really in the antiferromagnet. It's so-called Baxter staggered magnetization squared. I mean, it's not here. In this case, it's not the 1-point function squared. The 1-point functions are still zero in this phase, but the 2-point functions, the long-range asymptotics of the 2-point functions -1 to the distance times the number. And this number is called Baxter staggered polarization, and this is exactly this θ1 prime over θ2.
Okay.
Yes.
Yeah. Okay. Thanks.
Okay, I suggest we leave further questions and comments maybe for private discussions, and we thank our speaker again. And,